This is my video lab report for Lab 4 on oscillation. In this lab, we examined the motion of a spring mass system, which means that there's a mass attached to a spring, and we examined how it moved in an arc motion while also oscillating with the spring. While this motion seems to be complicated, we can break it down using some fundamental principles. Let's take a closer look at some of these principles. Here we have the equations for the force of gravity as well as the spring force. The F net equals both the spring force plus the gravitational force, because these are the only objects that are doing work in our system. The final velocity equation and the position equation that stem from Newton's second law, which we have learned previously. While here on the energy principle, we have the total change of energy equals the change of kinetic energy plus the change of potential energies of the gravitational and the spring. Our equation for kinetic energy equals 1/2 mass times the velocity squared. Back to our potential energy is mass times gravitational constant in the y direction. 1/2 times the spring constant times s squared, where s is the current length of the spring minus the relaxed length. Here, the equation where time equals 2 pi times the square root of mass divided by the spring constant is rather important in this lab because it allows us to observe the time between the oscillations and use that to solve for the spring constant, which we can see we move the equation to the other side. In this particular instance, because there is this motion, the change in energy equals the same as here. However, now we're also dealing with the change in thermal energy. After downloading our video file of the spring in motion, I put the video in Tracker and set up some calibrations in order to examine the motion and collect relevant data points. The video was recorded at 10.53 frames per second, and the calibration stick was set at 70 meters between the attachment point and this point here. While in the lecture video, we set the y plus direction is up and the x plus direction to the right. After all the following calibrations were made, I selected the center of mass of the actual mass on the spring in order to find my data points that we can see here, where the time step is in the leftmost column, the x position in the middle, and the y position in the right column. These data points produced a plot where this is the y position of the mass and this is the time, so we can see that the oscillations occur in this manner. After using Tracker to examine the actual motion of the spring mass system, I then began working on a computational model for comparison. Using ViewPython, I created this model by plugging in relevant data points. For example, the delta t being the time between frames, the gravitational constant, the spring constant, which we found using our equation for time between oscillations, the length of the relaxed length of the spring, which was measured, and the new length, which is obviously observed. In the calculation loop, I used the equations that we derived from our momentum principle as well as our energy principle, which we can see down here. After running this model, I produced a visual representation where this black arrow represents the gravitational force and this blue arrow represents the spring force, and this line representing the path of the mass on the spring. This model also produced a graph where we can see the change in kinetic energy by the blue line, the change in potential energy of the spring in the red line, change in potential energy of the gravitational force with the green line, and what would be considered to be the total change of all of the kinetic energies and potential energies of the system. After collecting data from the observation as well as the experimental model, I placed both of the data points into a graph for comparison here. As we can see, there seems to be some sort of minor discrepancy between the model and the observation. But what could that be? Does that mean that the energy principle isn't satisfied? Well, for our model, the energies that are taken into account for our system does not include thermal energy, whereas the observation, of course, does, because it has to abide by the natural laws of physics. Nor does the experimental model take into account the drag force that would happen in real life. The second half of what does it mean, I estimated the period of oscillation for our x position and the y position based on our observed motion. I calculated this by finding the average time between oscillations. The assumption that the x and the y oscillations would be equal to each other is incorrect, because the gravitational force is always acting in the negative y direction, whereas the spring force is acting from all different directions as the mass moves around. And that's all I got, so thanks for watching.